Today we're going to go over the rotational partition function. So you probably detect a trend. We did translation last time, rotation today. Not Monday, but on Wednesday we'll do vibrational partition function. And today we're going to talk about the homework problem that's due, because it's a real world problem of a two-level system. Okay, so you may say, well, this two-level system, Boltzmann distribution and everything's not that useful. No, it absolutely is. And here's an example. So on the homework, you have this example here of the internal rotation of 1,2-dichloroethane. So let's draw a few little figures on here so that we can see what we're talking about. So do y'all remember Newman projections from organic? Okay, so here in the minimum, if we've got 1,2-dichloroethane, okay, that means it's a sigma bond in the middle and it can rotate. It's not an ethene, which would be a double bond. Okay, so we have, looking down the carbon-carbon bond, in the back we have a chlorine, and 120 degrees from that we have a hydrogen, and 120 degrees from that we have a hydrogen. Okay, and then we draw the lines through the center to show the carbon in front. So at 180 degrees, the chlorines are opposite of each other. Does that make sense to everybody? Okay, so that's the Newman projection for the lowest energy structure. Oh, goodness. Thank you. So that's this one. So you can see now the 60 degree and the 300 degree would just be the ones where the chlorines are still in a minimum, but like, you know, this angle here from chlorine to chlorine is the angle that we're showing, the dihedral angle. So I'll just call that theta. So this is theta. So when it's at 60, the chlorine is here. And then that's E1, right? And then when it's at 180, it's here. That's E0. Is it okay if I just mark the energy levels on here so we don't have to redraw the whole thing over and over again? Everybody understand what I'm doing? Okay, and then when it's over at 300, then it's over here. We're back to E1 because it's the same energy. And that's an example of degeneracy, right? It has the same energy whether it's on the left side of the chlorine or on the right side of the chlorine. So I'm just really showing you the positions. Now, these positions, E2 and E3, they're still energy positions, but they're not bound states. Like the molecule can't stay here. It's going to slide down one side of the hill or the other, but it's still an important place. So a lot of times we'll label it as an energy level, but that doesn't mean a molecule can stay there. Okay. And so this would be E2 if it was, you know, the chlorine's coming along and it's bumping over this hydrogen in the back, that's E2. And when it bumps over this hydrogen, that's also E2. So do you see that? It passes over this first E2 at 120 degrees, then it goes down to the minimum, and then it bounces over the second E2 when it goes past the hydrogen, and then it's in this local minimum. And then E3 is when the chlorines are on top of each other. That's this top one. Okay. So a lot of students, when they start the homework, they will get in here and they will put all of those energy levels in and do the Boltzmann distribution and treat it like a four-level system with degeneracy in the middle. Do you see how it's a four-level system? E0, E1, E2, E3. Okay, and then you've got degeneracy on E1 and degeneracy on E2, but that's not the right way to do the problem because we're only interested in the bound states, where the molecule is going to sit. And the molecules are either going to sit fully opposite of each other with the chlorines, or they're going to be in the 60 or 300 degree location. So just do the bound states for this problem. So this simplifies to this problem right here of a two-level system. You've got 0, and the E1 is at 50 wave numbers. So energy here and wave numbers. And this 50 is doubly degenerate. So there's your two-level system with degeneracy. But it's a real situation. It's the internal rotation of the dichloroethene. So with that, you can set up your table and do your Boltzmann factors and calculate the partition functions and everything like that. Now, I think we go all the way to the equilibrium constant. So when you get to the equilibrium constant, you're going to calculate a probability of being in state 1, and you're going to have a probability of being in state 0. Your equilibrium constant, another way to calculate it would be that P1 over P2. If you want to know what the equilibrium P0. If you want to know what the probability of being in, the gauche side. So if you started the experiment with all totally opposite, like 180 degree, and that was your reactant, and then you let it go, how many would be in the products at state 1 over time? You could calculate that equilibrium constant and see. So those are the problems that are going to be asked. I mean, you're going to have to calculate Q. You're going to have to calculate, the probability of being in state 1, P1 and P0, and all of those things. Okay, so it's not that bad of a problem, but it's confusing to the students. The first time I did this problem, I put it on the exam. Oh man, everybody failed it because they didn't understand that this was just a simple 2-level problem with degeneracy. Okay, so then I moved it to homework because I think it's a valuable problem. It's a realistic problem, and yet it's still a simple example of a 2-level system with degeneracy. Okay, so that'll get you all set up for the homework. Yes?
For E1, why is that a lower energy level when the two chlorines are so close together?
Okay, so let me draw it for E1. So when I was trying to label these, Newman diagrams, I'm just following the chlorine and letting the hydrogens go with it. So here at E1, the chlorine is here, and then this is now a hydrogen, and this is a hydrogen. So we're moving the whole front atom around, and so it's lower than when that chlorine bumps over the hydrogen. So you see, it's still pretty low energy because it's in this gap. So on the back side, well, let me just draw that one. So we've got a chlorine here, and in the back side, you've got a chlorine there. And yes, they're pretty close to each other, but there's still a gap there because there's another hydrogen over here and a hydrogen over there. So this is 60 degrees, roughly. And so this is given E1. And then if it was going all the way around, it'd be 300 degrees as well. Yeah. And you're just saying, why is it low energy? Because they're still close together?
Yeah, I thought that if two heavy atoms are close to it, that would be higher.
Yeah, and it is higher than the E0. Okay, yeah. Now, whether these numbers are accurate, like 50 and 100 and 200, I just made those numbers up. So, yeah. So it may not be. It may be like maybe steeper and just a little bit lower, and then a little bump, and then a big drop down. So. Yeah, so that's what I mean. A lot of times, like on homework problems, we'll make up the numbers because the specific number of 50 wave numbers isn't important, but the picture is accurate. Yeah. And you can scan this in Gaussian and kind of get a measurement of what it would be in computational chemistry. That's the nice thing about computational chemistry, is that you can do things you can't really easily do experimentally. Like you can hold it in one of those positions where it wouldn't stay and calculate that energy, sort of a transition state between the two. And you can do that very easily in Gaussian. I say it's easy. They crash a lot, so you have to babysit the program, but you can force Gaussian to do it. Yeah. Okay. So hopefully that'll set you up for success. All right, now we talk about the rotational partition function. And we're dealing with the rotational energy levels now. And here we have the energies as they depend upon J and on the rotational constant. So we're going to be dealing, in this case here, with diatomics. Okay, so we're using the diatomic rotational energy equation, that B times J plus 1, which should be familiar to you because we did the carbon monoxide lab and all of those labs with diatomics last fall. What's interesting too, though, is diatomic or rotational energy levels, this G of J. Remember, the J is the quantum number for rotation. That's this piece. And the degeneracy goes up with J value. And we actually see this. You guys are familiar with this, only you call it L with the atomic orbitals. So for an S orbital, L is 0. And then for a P orbital, L is 1. What's 2 times 1 plus 1? That's 3. That's the degeneracy of the P orbitals. And then for a D orbital, L is 2. And what is 2 times 2 plus 1? That's 5. And that's the degeneracy of the D orbitals. So the degeneracy we're familiar with the orbitals and the L angular momentum quantum number is the rotational degeneracy of the electron around the atom. We don't like to really talk about it much because we don't want you guys to think incorrectly that it's like a planetary system where you've got that electron just rotating around the nucleus, but that is the degeneracy of rotation, is 2J plus 1, or 2 times the quantum number plus 1. And so in electrons rotating around the nucleus, that's L, the angular momentum quantum number. And for a molecule rotating in space, it's the same. It's rotation. It's 2J plus 1. So that's what we get out of the degeneracy. So now G is a function of the quantum number. So we have that piece in front. So we could, if we were in Excel and we just had 5 or 50 energy levels to calculate, we could put that equation in and we could sum that column and we would get Q. Okay. And it'd be temperature dependent because of the Boltzmann distribution. Now, once again, we can do this switch from a sum to an integral if we integrate over dj. So we're looking at this and we're saying what the difference in rotational quantum number is infinitesimal. So we're going to integrate over all the quantum numbers that we have, and we end up with this high temperature approximation. So it's a very, very simple result. It's KT over HCB. This B is that rotational constant. If we put all of this piece right here together, because that's a constant for the molecule, then we call that this rotational temperature. So we have the rotational constant. If we convert that over to Kelvin, then it's called a rotational temperature. And it's just converting units. We're taking the rotational constant, saying wave numbers, multiplying it by the speed of light, Planck's constant, dividing by Boltzmann's constant. So we're just changing it by all these constants and changing the units to Kelvin. That's convenient because then we can compare it to the temperature of the room in Kelvin. So we have an easy comparison. So diatomics are the smallest molecules, right? And here's the rotational constant. What do we have in that denominator? Is the mass term, or the moment of inertia. The moment of inertia is the reduced mass times the bond length squared. And so for larger molecules, that moment of inertia is just the mass of each particle times the distance from the rotating axis squared. Okay. But the point is, mass is in the denominator. So if we have big masses, we have tiny rotational constants. Let's look at the rotational temperature again. It's directly proportional. So theta B, all right, if B goes up, theta B goes up. Okay. And the same with if B goes down, theta B goes down. So what that means is the temperature, the rotational temperature goes up if the rotational constant goes up. And here, just a review for the rotational constant. This is that slide from the fall where you take all of those constants and even the conversion factor from meter squared to angstrom squared and Avogadro's number so that you can use grams per mole here, and the conversion from grams to kilograms, so that you can use masses from the periodic table and bond lengths in angstroms. And so this is just a really nice consolidation of the rotational constant. The 16.8576314. That's all of the NIST numbers as far out as we know them, and then you can use the reduced mass and the bond length in terms of angstroms and grams per mole. So that's always a good thing to have for your note card. And so diatomic hydrogen is the molecule with the largest possible value of B, right? Because hydrogen, it's mass of 1, okay? So it's going to have the smallest reduced mass, which means B is the largest. And so anything larger than hydrogen is going to have a smaller B, and it's going to be a really small rotational temperature. So what we're trying to do is figure out what the partition functions would be for all of these. Okay, so here's B, the Boltzmann constant can be used to convert any energy value into a temperature value. So we can convert all of these into temperatures. And so what's the rotational temperature for hydrogen? 87.5 Kelvin. And they said that the high temperature approximation, that integral, is good when the room temperature is 10 times the rotational temperature, or the 10 times the thermal wavelength, those kinds of things. And so here at 10 times this would be 800 Kelvin before the partition, that integral is valid. And so that's pretty hot, okay, for hydrogen molecules. So we might see some quantum effects for the hydrogen rotation until we're really, really hot. But all the other molecules, this is, look at HCl. Its rotation constant is 10, or even something like I2, 0.03. So what's 10 times this? Well, 0.3 Kelvin. Oh, well, we can convert this over. So let's do that. Let's do the rotational temperature for iodine. So you take 0.03735, and you just divide by 0.695 wave numbers per Kelvin. So it's 0.05. So when we get to 0.5 Kelvin, we're already at the high temperature equipartition for iodine. So we're never going to see quantized effects from iodine's rotation in terms of how it stores heat and those kinds of things until we get down to really, really low temperatures. Okay. We did notice that too in iodine when we did the iodine lab. Remember, those little bumps, those were the vibrational levels. We couldn't resolve the rotational levels because they were so close together. Okay. So let's look at a molecule. I just put in Gaussian. This is hypochlorous acid, if you want to call it that by its name. Here's the output that you get from Gaussian. Now, the nice thing about Gaussian is it tells you in the thermochemistry section what isotopic masses it uses. And that's the other thing, too. Like you use for, say, the carbon monoxide lab, you had to use the isotopic masses for oxygen and for carbon. Here, it's telling you which masses we're using out to 5 decimal places. It says it's an asymmetric top. It's pretty close to a symmetric top. A symmetric top would have things like for a symmetric top, like A would be greater than B and B would be equal to C. Okay, or so that would be for a skinny top. Something that's linear, okay? Or something that was almost linear, like alene. Do you remember alene? It had 3 carbons and 2 hydrogens on each end. It's really almost a linear molecule, but not quite. But that would be a symmetric top, has 4-fold symmetry. You could also have A equals B, and that be greater than C. And that would be for a fat top. And that would be like benzene. So benzene is a fat top, right? Its symmetry axis is a C6 axis. And so A would be the flipping of that plate. It's like a plate. And it could flip around the x-axis, it could flip around the y-axis, and those would be the larger moments of inertia, and then spinning around that c-axis would be the smaller one, and that would be the fat top. So look at this molecule. None of these are equal. So B is not equal to C and A is not equal to B, but they're close. These are close. Okay. And that's kind of interesting. So A is greater than B and B is almost equal to C. So this is almost what we call an accidental symmetric top, right? It's very close to being symmetric. Can you tell from those rotational constants here? These are in Kelvin, okay? Here's the rotational constants in gigahertz. That's what Gaussian produces, okay? We can convert that to wave numbers. I think I have that in the notes. Okay, so here's our A value in gigahertz. So 597 gigahertz, right? A hertz is a cycle per second, so that's hertz. Giga is 10 to the 9. So this is the same thing as this. Divided by Avogadro's number in centimeters, divided by speed of light in centimeters per second, 10 to the 10 centimeters per second. And so the per seconds cancel, and we end up with wave numbers. So 19.9. Now this whole conversion here is just this right here, 30 gigahertz per wave number. That's this gigahertz and this speed of light all put into one conversion. 19.9 wave numbers. Okay, and then converting that to temperature, we get 28.63. So we're just verifying, hey, we got the same thing, roughly. So which rotation is this? So this molecule can rotate around. We'll just call this, it's not really got a good symmetry axis, but we'll just call this the z-axis. And so then X is coming out and Y is in the plane of the paper. Okay. And remember that rotation, the mass that's rotating, is in the denominator of the rotational constant. So that means for the smallest mass of rotating, that has the highest rotational constant. So this is obviously the highest rotational constant. So which rotation do you think that is? Rotating around X, rotating around Y, or rotating around Z? Okay, because what's moving if it rotates around Z? Only the hydrogen. Yeah, so the A rotational constant is aligned with the Z-axis. So when we're rotating around the Z-axis, that's the moment of inertia of axis A. And that's, so this rotation here is A. So what we would do is we'd say, in this case, Z equals A, X equals B, and Y equals C. Now, if you were taking a graduate spectroscopy course, we would get into all of that and how we label A, B, and C, but it's not always X, Y, and Z is A, B, and C. You have to figure it out, like we just did. We had to look at it and say, wow, we've got one unique rotational constant, A. It's got to have the lightest mass. So which rotation would have the lightest mass? And so we were able to determine that pretty easily. And it didn't matter which B and C is because they're pretty equal. If it was a symmetric top, they would be equal. So whether X or Y is B and C doesn't matter. But you have to find the unique one. Anyway. So let's look now at the 3D partition function. The partition functions are, we kind of just jumped to this. We didn't derive it, so hopefully you're okay with that. The partition functions for all of the motions are multiplicative. So let's write this out. So partition function total is equal to the product of all partition functions. So instead of the sum, it's the product. So it's Q1 times Q2 times Q3. And so if we have 3 rotations, then it's going to be the vibrational temperature for each of those. So these are our 3 rotations. And this is our temperature times 3, right? Because the partition function is T over theta A for rotation A, and T over theta B for rotation B, and T over rotation C. Okay. And so this is B for a nonlinear molecule. For diatomics, it's just T over B, because B equals C, A is 0 and B equals C, and then we have T over B and T over B again, because the rotations are the same, and then so that's T squared over B, theta B squared, and you take the square root, so the squares are gone. So that's where the whole square root went. It was T squared to the square root and theta B squared to the square root. I don't know where the square root of pi went. So from here to there, still haven't, I don't know. But these are pulled out of the book. And so I should track that down. But anyway, this is what we have for diatomics. There's only 2 rotations for diatomics. Maybe some enterprising person on YouTube can put that in the comments if they know that. Okay. All right. Now, what's this sigma? Well, remember when we do statistics, we don't want to overcount. So I'm trying to think of an example of overcounting. But because this like A2 type molecules are very, very symmetric, sigma is 2. For AB types, it's 1. For benzene, like all of the different equivalent ways to write benzene, the sigma is 12 for benzene. So the symmetry number takes into account the symmetry of the molecule, and it's kind of like a degeneracy term, right? We don't want to overcount the possibilities if they're not distinctly different. And so that's why it's in the denominator. So it's preventing overcounting. And so the symmetry number prevents bad overcounting. Since we're doing statistics, we don't want to overcount the possibilities. Okay, so that's the rotational partition function. Okay, and remember, at room temperature we have around 200 wave numbers of energy available, and so we have all of these over here. And room temperature is going to excite these rotational levels quite a bit. The only one that's not super excited is the hydrogen. But if we have 200 wave numbers of energy, all of these diatomics are going to be very excited and have lots of population in the energy levels. So again, why do we care? Well, this is thermodynamics, and that's where we store energy. So we can store energy in translational motion. Remember, the argon had like 10 to the 30 energy levels populated at room temperature. The rotational levels are kind of intermediate. We can detect quantized effects, maybe not at room temperature, but at achievable temperatures in the lab. And so we still store a lot of energy in rotation of molecules. Okay. And here's the partition functions that we get out of Gaussian. Gaussian writes scientific notation in a really weird way, because it started out with the original programming language was Fortran, formula translation, a way to get a computer to do math. And their original way of writing scientific notation was like this. So this number here, 0.3 times 10 to the 5, okay, that's scientific notation. This just means times 10 to the 5th, okay. So it's 0.3 times 10 to the 5th. A little strange, okay? But that's how those are written out. And you can see that here's the translational motion. It's times 10 to the 8. And then here's, let's see, where's rotation? Rotation is right here, times 10 to the 4th. So it's not as big as translation, but it's still pretty big. So at room temperature, this molecule has a rotational partition function of 0.24 times 10 to the 4th. And so here we can take all of them, put together. These were the translational temperatures, the rotational temperatures from the previous slide. And what do you know? We get the same number, 2.4 times 10 to the 3, or 0.24 times 10 to the 4th. Okay, so we're checking Gaussian's math, which is unnecessary, but it's still fun. Get bored on the weekend, that's what you can do. Okay. All right. So here's how it behaves in terms of with temperature. So way down at this end, we would do a discrete sum. So if we're really at low temperature, we would go ahead and just calculate the rotational energy levels, do it in Excel, add them all up, be sure to take into account the degeneracy. This Boltzmann term gives you the contribution to each energy level at that temperature. Sum them all up and you've got the rotational partition function. But notice it starts to approach a linear equation that just shoots up. And so at the higher limit, as temperature gets above 10 times the rotational temperature, then it just becomes this equation here where you've got temperature over the different thermal rotational temperatures. Okay, so let's do a Kahoot to see how well y'all captured all that information. But before I do that, are there any questions? There's a bit of a review is kind of nice, I think, with the rotational constants. You remember all of that? Okay, good. So let's do this.